SwayamPrabha. Digital India. Educated India.
Yeah, welcome to lecture 2 on day 10. Welcome from my side. It's, I think, an excellent transition from lecture by Professor Shankaran to the following material, because I think it was made very clear and very transparent why this sluggish diffusion of high entropy alloys, which has been proposed as one of the really important core effects, is so important also for the applications, especially in high temperature applications. We now will basically analyze what's behind this hypothesis of sluggish diffusion, and maybe also behind really the prospect of applying them in the future, because we will certainly not see these very model type alloys, FCC based, not so high melting temperature in real applications, because they would be just too expensive to make. And at the same moment, they would not present sufficient benefit for their use. This is, I think, different for high entropy, for high temperature applications, because there is a huge demand, right? Especially on coatings. If you think of making a better engine for an airplane, not only if you think about military, but also about civil applications. If you raise the temperature by a few degrees, you can save a huge amount of the fueling up. So this will be saving money as well as saving the environment globally. And this is true actually for many of the high temperature applications. Also worldwide, except some countries like Germany, we still have nuclear reactors going, right? And there is a very big problem in maintaining them over many years. Can you imagine why? What happens in a nuclear reactor? What limits its lifetime? The radiation, yes. You basically have very hard radiation, meaning very high energy radiation impacting with your material. What happens? If you put a steel sheet around your inner part of the nuclear reactor, it's called the first wall. And it doesn't matter whether it's a fusion or a fission reactor. It will heat up the material. More importantly, it will cause Frankel type of defects, right? So it will knock out atoms from their position. They go to the interstitial lattice site where they don't like to be, and create also a vacancy. So there's an interstitial vacancy, self-interstitial vacancy pair. And there's more and more created, and that means that causes embrittlement. Also other processes, dislocations are introduced, and so on. And that all basically leads to a whole range of failure mechanisms. Bubble formation, so you form voids, you embrittle the material. You have the material swelling actually because of the extra excess volume it creates. And actually this can lead to popping the head of the bolts holding everything together off. It happened once in Israel, where the first wall was falling down, and then the whole nuclear radiation is exposed to the outside. You don't want to have this happening. And so it's important to have a radiation-hardened material, meaning similar approach as Professor Shankaran just told you about. It should be a material which can withstand degradation up to very severe conditions. High temperature would be one example for these conditions, but also going to very strong doses of irradiation is another one. So it would be highly beneficial to have now a new way of designing alloys and materials which can withstand this to much more extreme conditions, higher temperatures, higher irradiation doses, influences. But we have to see, is it based on reality? So let's come down to Earth from space. So far, correctly, Professor Shankaran has told you what is being thought and being written in most of the papers in literature and the books out there. But I think I would like to analyze the situation a little bit more closely. So many remarks in papers really support sluggish diffusion, as just said. But many of those are based on secondary observations. So people did not measure diffusion in itself, not even interdiffusion or chemical diffusion, but they looked at stability of precipitate, stability of microstructure, stability of a small grain size, and related their observation, which are true, whatever, all the important points Professor Shankaran has just told you are true. These materials can withstand a certain grain size up to a higher temperature. They can keep a yield strength up at a high level up to higher temperatures. But to infer from these measurements that it's due to sluggish diffusion is a hypothesis, scientifically speaking. So they are indirect observations, which is very important. So it's not a proof, it's just a suggestion, right? And most of the time, because of the application relevance, these observations were done on high entropy systems which belong to the refractory high entropy systems family. So it means melting temperatures are very high. The investigations are normally done at temperatures where service temperatures are required or where facilities are available, meaning that the homologous temperature at which these tests were done are not so high. So actually diffusion doesn't play a role at these low homologous temperatures. In any case, you will have, yes, sluggish diffusion, but you would have sluggish diffusion also if you would use pure tungsten and do these tests at these low temperatures. And so it's not really the meaning behind sluggish diffusion as in the high entropy context. Yeah, only one very early and very highly quoted and cited paper was there when most of the papers were written, and people refer to this in the papers also, where people measured diffusivity in this Cantor alloy, right? But as I told you earlier, this was done also not measuring tracer diffusion, which can be interpreted easily as self-diffusion, but their chemical diffusion, interdiffusion in a diffusion couple was measured. And now let's think about, is this really a good way of testing the hypothesis? And well, maybe it's not, because what sluggish diffusion really means would be sluggish tracer diffusion when we think of how to measure it experimentally. So when you say, okay, the material's transport of the atoms inside of a material per se, due to the design of the alloy, is sluggish, it means the self-diffusivity would be sluggish. This means if you want to measure self-diffusion, you do tracer experiments. What has been done is this. The chemical diffusion, because it was occurring in a gradient of concentration or chemical potential. There is a large difference between these two diffusion coefficients, and they are interrelated by what is called the thermodynamic factor. And we are going to talk about this now in a little bit detail. So let's consider the diffusion would be taking place in a non-ideal binary substitutional model. Non-ideal means we do not take the ideal solution model. We have interaction parameters between A and B, and that means that we have to, in order to describe the chemical potential, use the full approach relating the chemical potential also to the activity and activity coefficient. If this would be for the ideal solution, how would the equation look like? What's the activity? Yes, exactly. Yes, and activity would be just composition, right? Yes, exactly. When we now write the activity at the activity coefficient, we can use classical standard textbook thermodynamics. So we arrive an equation by chain rule for the first total derivative of the chemical potential of one single constituent A with respect to composition fraction X. Since the concentrations or the sum of all concentrations of all the constituents is always fixed because it's one, right? I mean, we have conservation of atoms, of matter. Then we can just plug these terms into the equation and proceed further. Here we already see that we get now a slightly more complex relationship between the concentrations of A and B and the chemical potential of one constituent in the alloy, right? This is very important. When we now think of first Fick's law, then we can just replace these terms into the equation, which has been derived before, just again based on simple flux approximation. Plus conservation of matter. You know that basically you put in an artificial plane and you say whatever goes through the plane from the left needs to come out on the right and vice versa. Then you have the first Fick's law. Which means that we can now put the equations on the first page, especially the last one which I circled, into the flux description. And what we get then with a little bit rearrangement is this term, right? And if we again use the definition of chemical potentials for a non-ideal solid solution with activity coefficient, then what we get here is this equation. There already this term is included. So this logarithmic, what is it again, the English word? Derivative, in these square brackets relating to the derivative of the chemical potential. And this is then again slightly modified, and what you get is the connection between chemical and tracer diffusion coefficient, and it's related by this term in the curly brackets, which is the thermodynamic factor. And this thermodynamic factor basically takes into account that when you have interacting atomic species of different kinds, here only two, but in a high entropy system more than that, that the diffusional transport of constituent A depends also on how constituent B is transported. Right? So it's kind of correlating the diffusivities of the constituents. And you can see that when you now do an interdiffusion, well, maybe I write this one first. If you now do an interdiffusion measurement, and you get this right. So if you apply a diffusion couple, you have two different concentrations on both sides of the couple. You do the thermal annealing and so on. What you see as a result is the result of this chemical diffusion. If you now want to infer self-diffusivities from that, you need to know and you need to take the thermodynamic factor into account. And only in dilute solution you can do this based on simple thermodynamics as included here. High entropy errors are by definition not dilute. So it means you are not allowed to do this. And this was done in this paper, which is so highly cited. This is why it could be true, it could not be true. We don't know before we measure properly. So we want to really do a proper job, do volume diffusion measurements using the radio tracer method. We measure tracer diffusivities, and because we know from experience and we would expect from theory that these small isotope effect having different number of neutrons, maximum difference 2 neutrons per core, would not affect the diffusivity much. So we can, with good quality and accuracy, say tracer diffusion coefficients are self-diffusion coefficients. So we measure self-diffusion. These are then the meaningful experimental data to discuss and analyze if diffusion is sluggish. You know how it works. This is what's done. And this gives you tracer diffusion profiles measured firstly in a single crystal, high entropy alloy, which is a typical FCC Cantor system. You can see all of the constituents have been measured because nicely for all of them good tracers are available. And you see that here the kinds of concentration of marked atoms, so the relative specific activity, the decay product density, so to speak, is plotted as a function of depth squared. Right, so we do the slicing, and if we go further into the material, y becomes larger on a linear scale. We plot it here on a quadratic scale or against the penetration depth squared, because we assume that this is just following the typical Gaussian solution for the diffusion problem because of the specific way we conduct the experiment, that we apply a thin layer of tracer solution. And this is again written here. So this is how we describe then mathematically the diffusion, right? I mean, this is basically just the boundary condition as well as the solution of Fick's second law. Yeah, and so we know there is only volume diffusion here, and then we can use the Gaussian distribution. And then from the solution of this diffusion problem of Fick's second equation, we know already how to plot the data, right? We need to plot it against the penetration depth squared. And this is why the plots here are done in the way they are, because then you can directly infer from the slope of the fitted data how large the diffusion coefficient would be at this particular temperature. So it means if you want to, and we always want to, analyze diffusion as a function of temperature, that's really the important point, right? To know how high can I heat my alloy? How long will it be stable? And this is all depending on the activation enthalpy, which in the end you want to deduce. For this, we need to know the temperature dependence. Then we make an Arrhenius plot. Diffusivity is a function of 1 over absolute temperature. From the slope, we get the activation enthalpy. Then we know all what we need to know. We even know then the magnitude of the diffusivity at the different temperatures, or we can calculate. But this means that one has to do many experiments, and each experiment at each constant temperature is an individual experiment done, then sectioned, evaluated, then you only get 1D, right? So you have to do more than one experiment. Then one needs to deconvolute the profiles which you measure from induced artifacts of the measurement. I told you, right? Whatever you do, what you mechanically grind, or you cut, or you section by sputtering, you will have some grinding in effect. So you will mix some of the marked atoms from the surface more into the depth. And this is where you basically use a zero profile to correct your experimental profile. This is shown here. This will be has been done for all the profiles I later show to you. So it has also always been subtracted. So it means zero profile, when you look at it, this is a logarithmic scale always, right? That is important. So it means the zero profile is much, much lower than the obtained profile. And so here in these very nice measurements, I'm showing nice measurements obviously because we don't show the bad measurements. We then measure again if it's not a good measurement. Then you see that there is almost not a big difference between the reconstructed and the still convoluted fit to this directly obtained experimental profile. Yeah, so then going from volume diffusion in a system which doesn't have grain boundaries, we are now obviously interested in the real material. The real material would not be an artificial single crystal, but polycrystalline material obtained after some casting process or arc melting process or so. But in order now to analyze, is diffusion sluggish or not, we have to have a comparison, right? Sluggish as compared to what? And so the first comparison what we did is we go to a medium entropy alloy. And compare it to a high entropy. And it's necessary to anneal both systems at specific temperatures in order to induce diffusion. So we basically need to be sure that we are comparing the same things. We need to know the phase composition of both alloys, medium and high entropy system at each temperature where we are studying them. And these X-ray results show nicely and confirm that for these specific choices of alloys at the annealing temperatures chosen, both would be single-phase solid solution. Yeah, so obviously if you go to lower temperatures, there will be decomposition as we discussed a few days ago. This is the microstructure. So orientation, imaging microscopy by EBSD on the left side shows a rather random distribution, coarse grain size, homogeneous element distribution obtained here by EDS. And atom probe tomography confirms this. So we are sure that on all levels, length scales of the microstructure, from atomic, atom probe tomography, to really grain size length, which is of the order of many, many micrometers, we have a very uniform, homogeneous material in terms of its chemistry and chemical component distribution with a random texture, so no strong anisotropy in terms of orientation of grains. So ideally to do diffusion measurements. And this is the result of thermal characterization. Differential thermal analysis was done. Abbreviated as DTA, right? So you take a sample into a crucible, you have a reference crucible, you put it in a furnace, heat up, and any transformation in the sample will cause an asymmetry in the temperature field inside. So a temperature difference will occur between reference site and sample site, and this is picked up here as a signal. And since this is done in a quantitative way, it can be evaluated as heat flow as a function of temperature. And we see here basically what you do is you put a tangent to the part of the steepest slope of the signal, you put a tangent here, and this is then defined as the temperature of your transformation. In this case, these transformations are melting temperatures. Why do we measure this? Is this important to analyze diffusion? Think about homologous temperatures. These are different alloys. One is 4, one is 5 component. You see the melting temperatures differ rather considerably. So it means if we now compare their diffusivities later on, again, we have to worry how to do the comparison. If we do it just at the same absolute temperature, then we have one measurement done much closer to the melting temperature of the respective material as compared to the other one. Maybe this is not a good comparison. Maybe we should then normalize the temperatures of the measurements for each respective system by the respective melting temperature, and then we can do a good comparison on equal homologous temperatures. This is what we get. You see, your question was excellent, because this is what we get in reality if we go to any temperature which is not exceedingly high and close to the melting temperature. We get in one profile 2 contributions. And while one, the slower one, the process which is described by a intrinsically lower diffusivity, is bulk diffusion, and this will be showing up as the steeper part at lower penetration depths. So it goes down more quickly, and then it goes to values so that you can no longer measure, because there's too few radioactively marked atoms at the higher depths. And then there is a long tail, which is due to the grain boundary diffusion coefficient. And this is done again at constant temperatures, and then for the different constituents separately. So this shows you here the penetration profile of nickel. So you applied nickel as a tracer and did the experiment at one temperature, but then you have to do it also, if you want to be complete, for manganese, for cobalt, for chromium, and for iron. Right? So it means for each temperature, 5 measurements. If you want to get activation enthalpies, 5 measurements times the number of temperatures which you want to check. So it's quite some work, which was done here. And you describe then the profile by this very simple additive law that you basically get at any sectioning depth in your material a description of the total concentration of marked atoms just as a sum of the contributions from bulk and from grain boundary diffusion. So a kind of independence of the individual diffusivities. If we now do the evaluation and then go and jump to the Arrhenius representation, this is then again showing you the diffusivities as a function of 1 over temperature, Arrhenius representation. And this is done then for the 2 different alloys, medium entropy alloys on the left, high entropy alloy on the right. But on the basis of using the absolute temperature, not the homologous temperature here for the comparison. What can we see? Well, we see that basically the constituents in the 4-component system have rather similar diffusivities. Slope change a little bit, which means activation enthalpy for diffusion is slightly different for the different constituents, but the difference is not very large. Nickel is the slowest diffusing element in these materials, and this is the same also for the 5-component system. Cobalt and nickel diffusion there in the 5-component show a crossover, which is interesting for diffusion theory, and we will discuss it a little. But the main point is you do not see a lot of changes if you go from 4-component to 5-component, from medium entropy to high entropy system, except that the 5th added constituent, the manganese, is by far the fastest diffuser. So you would expect this, because when you look at the periodic table, manganese is really the most different atom as compared to all the other ones which are part of the 5-component Cantor alloy, right? So iron, cobalt, and nickel are very similar because they are basically in the same group, and chromium is nearby. So manganese, also from melting temperature and so on, electronegativity has the largest differences. And so it's also expected that the differences for the self-diffusion coefficient of manganese in the 5-component system would show the largest difference. Because of its lowest melting temperature, we would expect it at constant temperature to have the highest diffusivity. So in summary, nothing unusual. But you already see when you go from a more simple, conventional design of a material to a high entropy alloy design by adding new constituents, that the complexity increases, right? Because you add a new constituent with a new electron configuration, with new everything. And so the comparison can be made, but what you learn from that comparison is still up to debate, I would say. When we now look again at the individual tracer diffusion coefficients as a function of homologous or temperature, 1 over in an Arrhenius representation, then the system shows no crossover for chromium and iron, but for cobalt and nickel it does. And basically it also shows again small differences, but in tendency the diffusivity for the high entropy diffusivities for the high entropy system is reduced as compared to the medium entropy system. So one could say, yes, this is an indication for sluggish diffusion because the self-diffusivities at given homologous temperature for the high entropy alloys are lower than for the medium entropy alloy. Word of caution again, the differences are small. And if you would now, even in conventional alloying, add an additional element, alloying element with substantial concentration, you would also expect that diffusivity goes down on the same order of magnitude, less than 1 order of magnitude at given homologous temperature. So on a homologous temperature base, comparison between medium entropy alloy and high entropy alloy indicates a little bit more sluggish diffusion for or in a high entropy system. But the effect is small and in the expected range. So nothing which you would define as a core effect of a new alloy design strategy. Maybe I do this next week because I wanted to show this one here. So if we then again use a comparison, but now we go with the comparison using, in this case, again, the upper graph shown on the left side, homologous temperature as the basis for the Arrhenius representation, in the lower part, the absolute temperature, and compare now more widely. And just for nickel diffusion, and we compare nickel self-diffusivities in different matrices, meaning we go all the way from pure nickel up to the high entropy system. And you see here pure nickel is also this darkish black but dashed line, and the high entropy system is the dark black solid line. Yeah, what's your feeling? Would you write a paper on sluggish diffusion in high entropy systems based on these results? I would not recommend it because maybe the reviewers would shoot you down. So you see, it's all relative, right? So you can always find some conditions or some specific ways of comparing your data where you can certainly say, yes, diffusion is more sluggish. But you can also find comparisons and bases like homologous or absolute temperature and so on, where this statement is at least taken with a very big grain of salt, especially concerning the magnitude of the effect. So, because as I also indicated, there's also always the additional comparison one has to have in the back of the mind, that you have to compare it to the expectations just coming from normal alloying if you go from a binary to a ternary, let's say, right? And so this is, I think, really a nice confirmation that just stating diffusion in high entropy alloys is sluggish is at least very questionable. We will see later on next week that there is good examples from directly measured self-diffusivities that even show anti-sluggish behavior, so the opposite of sluggish, for other high entropy systems, particularly for ones that are actually used or useful for next generation applications. Yeah, so they are good alloys, they are a new alloying strategy, but I would say relating their behavior to sluggish diffusion is unfortunately not true. This brings us to a question I have to you. We could start the discussion today, but maybe we can continue next week, because I think it's very interesting when we just listened to Professor Shankaran's lecture today, right? There is so many effects that would be so easy to explain if the diffusion would be sluggish. Now I tell you diffusion is not sluggish, not more sluggish than it should be. So how to explain then the properties measured? What other effects could come into play? If you see, oh, well, great, the yield strength is maintained up to much higher temperatures. Wow, the grain size may stay small up to higher temperatures. All these effects which we really need to have to create, I mean, all this nanostructured materials business which is going on since, I don't know, 30 years or so, was always limited by, for example, having grain growth occurring at much too low temperatures. So having materials which are stable is fantastic for many, many aspects. But how to explain if diffusion is not sluggish? Yeah, I mean, the properties are measured, and I don't doubt the measurements, but we also have measured the non-sluggish diffusion, and I also don't doubt these measurements. So we have a conundrum, right? We have two experimentally certified facts, but they don't go together, right, easily. So we have to fight, and this is like how you think as a materials scientist in your working environment, right? Yeah, Cottrell logs, Loma logs are very, very easy. For those who have not been advanced to the, more higher studies on dislocations. Dislocations are line defects. They can interact in multiple ways. And some of these ways involve splitting up of a perfect lattice dislocation into partials. So one partial goes first and the other one trails it behind. If this distance, splitting distance, is large, there is a good probability for another split dislocation to interact with this split dislocation. And then basically a lock formation could form, which means there is a dislocation-dislocation interaction forming a product which is not longer, can no longer glide because it has a Burgers vector which doesn't agree with the lattice it's in. And this is stabilizing the dislocation structure. And so there is no diffusion coefficient involved. It is just because of crystallography that you stabilize defect densities. And also we have here this potential energy landscape, which is very complex, right? Because all the atoms are not correctly sitting on a given FCC site, lattice, site, because of the fact that you have all the interatomic interaction parameters being different from site to site. That makes also glide more complex. That makes interactions more complex. This gives you a more different range of how you calculate interaction products. Also, if a vacancy you want to jump from site A to site B, neighboring site, on this side it has maybe a different barrier than on this side, because there it's cobalt sitting and there it's manganese sitting, right? So it means these are intrinsic effects which I think, and this is my interpretation, are coupled to the local lattice distortions because of the alloy design. They don't necessarily affect in total volume, and as we later will see, grain boundary diffusion coefficients, but they affect storage capacity and retention of high defect densities up to higher temperatures in a non-diffusive way. And this might explain why yield strength is kept up at high levels up to higher temperatures. Grain sizes stay stable up to higher temperatures. So this is, I would say, my interpretation or my conclusion from this conundrum, that we say, okay, we see the properties are improved, but on the other hand, we see the diffusion isn't much changed.
Have you done any research back in the lab?
Yes, we did all these diffusion measurements. Yeah, no, I'm joking. We do this, and we also relate it to microstructures. Yes, yeah. But I will show you more on this the next 4 lectures next week, especially on how you can also test this hypothesis in a different way by not changing the alloy from a medium to a high entropy alloy by adding a new constituent, but by a more clever way, I think. always keeping the 5 constituents the same, but within these 5 constituents changing from a dilute alloy up to the high entropy system, and monitor then how the system properties change, going from almost pure single phase material with some minor additions up to the high entropy system. And then going to the last chapter of this lecture, which is how to analyze grain boundary diffusion in a multi-component system. And we will start with some diffusion theory as indicated in the first lecture on that, because you need to understand all the pitfalls there are in terms of doing these measurements. So with this, I think I would stop here. All right, thank you.